What's first?
Change over cost and sign.
So that's the first one.
Yeah.
So what is secant?
One over cost.
Minus
cost.
Yeah, because one thing is a fraction, everything is a fraction. Nothing bracket. Go again.
Same thing, one over cost plus.
Yes? And then this is the same thing, right? All right. Then the proof really begins here, right? Which side? Left hand side is clearly that, right? And I'm supposed to write this as one each and every division. That's all?
Cos theta over 1 divided by 1 over cos theta plus cos theta over 1.
And you did all of this, those who were stuck. Everybody else who were stuck got this part? Or is what this one that you're stuck on?
No, like Martin part of it.
So, what do I do with this? I need to simplify within the brackets of each of them, right? So what's the LCM in this first bracket?
Cos theta.
Cos theta into cos theta. Huh? So 1 times 1 is 1 minus 1 into cos, cosine times cosine, cos squared theta. Anybody recognize what's up here? Sine squared theta. You see how you must recognize it anyway you see. But this comes from 1 plus, cosine squared plus sine squared equals 1. Remember? So you have to recognize it in every form that's coming. Fair enough? But we don't reach there yet. I just testing to see if you readily identify it. Maybe that's where you were stuck. Never recognize that. Remember when you're stuck, you're not really stuck. You must look for the identity. That's the rule, you know. Fair? Over here, so you see LCM, cosine theta. Cosine into cosine goes 1. 1 times the original numerator. 1 times 1 put plus. 1 into that goes cosine times cosine squared of the theta. All is well? All right.
I'm sorry, if I have to upload the videos on the WhatsApp group, you know.
Why would I?
Because I recently come in the group, so I can't see the previous messages.
But I sent you see I sent a link?
Yes, I see one. I see 2 links.
Oh, one of them that says all your videos are stored here? Yeah. That's one you need permission for? Yeah. You did your click request permission? Yeah. You will be granted permission, Sean. Same thing for you, right?
Yes, sir.
But if it persists, then you let me know after like a day or so. You know? Good night, miss. See you sneaking in, eh? So, what do I have here? I have now one fraction divided by another fraction. So now this is?
1 minus cos.
1 minus cosine squared of the theta upon cosine of the theta multiplied by cosine of the theta all over 1 plus cosine squared of the theta. And it is easy to see that the cos cancel. So now I'm left with 1 minus
squared theta.
cos squared theta
Cos squared.
over 1 plus cosine squared theta.
And then
And then this is where some of us would have really been stuck. But then it's two ways. You either recognize that this was the identity of the bot, or you said, well, how far am I from the truth? See, this is what I'm working towards, and I realize that the denominator is the same thing.
Yeah.
So even if you never know what to do, it's obvious that this must have been, unless I'm keep on line, equal to sine squared theta. So put it on.
Pure theta.
But it's really because since sine squared theta
Plus squared theta.
is equal to 1 minus cosine squared theta. Huh? And if you transpose it, you see that sine squared plus cosine squared equal to 1. Right? So when you stop, identity is, right? Next one. So what determines part B?
1 minus cos squared theta.
There it is. What is it?
1 minus cos squared theta upon sine.
1 minus cos squared theta
Yeah.
upon?
Upon sine theta equals sine theta.
But that one is beyond the easy,
Yeah.
right? It's the two line up. Everything is already in sine and cosine. So left hand side would be 1 minus cosine squared of the theta upon sine theta. And by now, we should easily recognize that 1 minus cosine squared is sine squared, and 1 minus sine squared is cosine squared. So this is sine squared of theta upon sine of theta. That means one of that cancel that, leave with sine theta upon 1, which is sine theta equal to my right hand side. Cannot be easier than that. Question. This is separate and apart from the homework. If I ask you, what is sine squared theta? Two sine squared theta minus 2. What will you tell me this is equal to?
1 minus cos squared.
Huh?
1 minus cos squared.
A 2.
1 minus 2 minus.
You should go up with 2 quick, yeah.
It would be,
2 outside,
oh.
and then sine squared theta minus 1 inside the bracket, and then that's the difference of 2 squared. So 2 sine squared theta minus sine squared theta. Sine theta minus 1.
So you have said
plus 1.
2 into
That is sine squared theta minus 1, and then inside the bracket. Oh, you don't want to send it further?
no, I never said that. This is where you tell me to reach so far.
Okay, that's the difference of 2 squared.
Okay.
The 2 still outside. And then sine theta minus sine.
Negative 2 sine
theta plus 1.
squared theta.
Right?
Negative 2 cos squared theta.
You see why? You see it's rational?
Oh, the sine squared theta minus 1.
You not seeing it? Because the way you did it, you would have had it. You would have ended up with, if you did it like that, you'd have ended up with this. And then that looks simplified, that look, no. Clear? So what I want you to start recognizing is that you don't need to say 1 minus sine squared. What you need to see is that you see a 1 and I see a sine squared, and both of them have different signs. If that's the case, then you have to remember that a minus b is equal to what? Be careful. It's minus b, follow me, plus the a. Technically, write minus b first, and then this was technically a plus a negative b. Do you agree? So this is negative b plus a a. Yes? No lies. Then if I take out a negative out of this, then I'm left with b. And then be careful, if I take a negative out of plus, I'm left with negative. Check it, expand it. Negative b, negative times negative, positive a. That's all. So what I want you to remember now is that while addition can be flipped around, the negative can be flipped around. Just so, to flip around the negative, you need to stick a negative in front of the overall difference. So, you see how that works? So A minus B is not equal to B minus A, but it's negative of B minus A, right? So here, when I recognize this, all I would have done was to say, well, 2 times a negative 1 times a 1 minus sine squared of theta. Can you see that? Because I wanted to flip this around. But in order to flip it around, we know that subtraction is not commutative. Remember that? We did commutative? We introduced commutative in this class? No, that means that's not next class. That's next Saturday, right? But yes, we did.
Yeah, man.
In algebra proposition.
Distribution
With the and, remember we always said
Oh, yes.
P and Q equals to Q and P.
Oh, yes, yes.
That's what's commutative. That means you can flip around. The order doesn't matter, right? Same like 2 plus 4 equals 4 plus 2. That's what I mean by commutative. The order doesn't matter, right? So, but for subtraction, the order does matter, right? So we have to be careful. You have to remember that when you switch it around, just like that, we have to stick a negative in front of it. And but the 2 was already there. So technically what we have is negative twice, and we know what is in that bracket. Cosine squared of the theta. So this is negative 2 cosine squared of the theta. Food for thought, right? Everybody follow?
No, sir, where the one comes from? Plus one.
Negative 1?
Plus one, plus one.
We're plus 1. Where is that
I
plus?
said 1 minus sine squared.
This?
Right.
Flip it around.
Just plus one.
Sorry, 1. This is like A minus B.
Oh, I thought it was positive one.
So this becomes minus this. So this becomes negative
And one negative.
B minus A. You have seen that?
Oh, yeah.
Yes?
Yeah.
Flip it around. So in other words, instead of subtracting 1 from sine squared, I subtract sine squared from 1. But in order to do that, I need to stock a negative 1 in front of it. That's what you need to remember here in a simplified form. Right? So you need to know that if I say P minus Q, I know is negative in bracket Q minus P. Don't forget that. Right? So I guess the homework wasn't that challenging after all, because some of us didn't want to do the homework, right? And the third one, well, let me give you some time to write that off. What was this one?
Secant theta plus tan theta upon cotangent theta plus cos theta equals sin theta upon cos squared theta.
What's the first thing to do? The first thing to do. How many classes come by the way? How many classes just called? You're just coming, that's like last week.
Yesterday started.
Yesterday you started?
Yesterday started.
Oh,
About 5 class.
next week I'll ask you. I'll put you on the spot, right? So you'll watch the video. Have you gained access to the video set?
No, the same thing happened.
All right. What should I do? You don't watch the videos yet?
Wait, again, a few hours ago.
Huh?
I did the videos a few hours ago.
Next week I'll put you on the spot again.
So you said it's not going
Huh?
You break up everything, you can custom sign.
So again?
You break up everything until you see custom sign.
All right, so tell me what to write.
Break up the time into say,
Yeah, you break out the time too?
crossover sign or time.
You tell me.
Sign of a
All right.
They break up the sec into 1 over cut.
You're still guessing.
No, I should remember.
Mhm.
The cut.
It's not hard. This S and this S don't go together. That's why it couldn't be secant is 1 upon sine. So it's very easy to remember. All right, come again.
The cut is crossover sign.
All right,
Just crossover.
beautiful. And that is equal to sine theta upon cos squared theta. Then what?
You change the fraction into division.
Needs and Nevis division sign.
Yeah.
But in other words, I'm saying the proof starts here, right? And now I'm taking a look at the left-hand side by itself. Is that so?
Yes.
All right. So I have 2 brackets separated by a division sign. 1 upon cos plus sine theta upon cosine theta. And then this is cosine theta upon sine theta plus cosine theta upon 1. For those who are new and didn't get to watch the video, you must be wondering why I do that. So it's a rule that we came up with, and we said once we're proving something, the first thing we want to do in trigonometry is to see sine and cosine only when we're proving. So that's our way of getting through the thing without bucking our toe too much, right? The second thing was we start with the most complicated of the 2 sides. Because in proofs, I cannot take anything from one side to the next, I am automatically incorrect. Fair enough? And then, because
Just repeat, could you repeat how you remove the tan?
the tangent is sine upon cosine. Every day and twice on Sunday. That's what
That's the
something,
ratio. Oh, that's when we go. Yeah.
right? It's something for you to know, right? And we did it when we introduced the graph and all that stuff, and we, right?
Yeah.
Good. And then because cotangent is 1 upon tangent, then it's a flip of the tangent, which is cosine upon sine. Secant, you're going to learn that that's a new thing, just like the cotangent, is 1 upon cosine. And the cosecant, this one is the only one you never see. Cosecant of an angle is 1 upon sine of that angle, right? So those are all things you're going to see in the video. You don't necessarily need to write them down. No, you write the notes as you watch the video. So that's what we did here. And then, if I will start with the most complicated of the 2 sides to simplify, to see if I can get to this. Whenever I have a fraction and the numerator and or the denominator are themselves fraction, I want to simplify it in a nice way. So I keep the numerator and then I put a division sign, my niece and nephews division sign, and then the denominator. Fair enough? All right. So that's just our nature by now. Right? Then by Bundas or any other algebraic law that you know, we need to work out the brackets first. So we're going to look in the brackets and I'm seeing 2 fractions of the same denominator. And because they're of the same denominator, I keep the denominator and group the numerator. That's what the rule is, huh? And then the LCM here is different, so I can multiply them, or I can take the larger one technically. The larger one is the sine, because 1 can go into everything. So I take the sine theta, and then sine into sine goes 1, 1 times the original numerator is cosine theta, plus 1 into sine, goes sine times the original numerator, sine theta times cosine theta. Is that true so far?
Yes, sir.
All right. Then, what do I do? No, you can't start much of it because all we're doing is routine stuff. Now I have two. This is one single fraction. This is now one single fraction. No matter how ugly it is. Is that true? And how do I divide two fractions? Huh? I reciprocate the second piece and change the division to multiplication. Eh? So, don't let the question intimidate you. It will always look ugly. Right? Change that to multiplication. Sine theta upon cosine theta plus sine theta cosine theta. Unfortunately, nothing looking like it canceling so far. So you want to believe you're stuck, but you're not stuck. So, what are the two main? So, am I saying any identity for starters? No.
No, we're not seeing that.
All right. So, can we simplify? What are the two main modes of simplification? Factorizing and finding LCM. But clearly, there is no LCM. So, is there anything on the board that can be factorized? I can take out cost out of this end. If I did that, if I take out a cosine theta out of this, what is left?
1 plus sine.
You agree? Yes? Numerator times numerator, sine theta. Denominator times denominator. So what do I need to remember? That when I stop, I need to do one of three things. Look for the identity. There is none. Try to simplify further before you abandon this side. Right? And what does it mean to simplify further? It means look if there's anything to factorize or find LCM for. Yeah? Which is basically the only two modes of simplifying. What do you go do that? Any clearer? So you're new?
Yes, sir.
Where are you coming from?
Women.
So where you come from there? You doing math at 211?
No.
So this is an extra subject. When you're schooling up class, you're aware of that, right?
Yes, sir.
Did you add much?
No.
Alright. So you're going to get access to the videos, which is around 10 videos in total. Around that? Probably around 8 videos in total. We're not gone 4 weeks yet. So that's good. So you have less than 8 videos to watch. 8 videos times 2 hours, right? So you have a day to catch up. Fair enough? Saturday is module 1, Sunday is module 2. Hence why we're unsure and unsure, right? But I hope that you'll catch up by next week. Good? The videos. So you can watch 2 a day. That's reasonable. I'll add you to the WhatsApp group and you'll watch the videos there. Right?
Do. Can you get some stuff? The business.
Yeah, myself, what is it?
But you know, there's something good.
No, you know, say, it's fair enough.
Oh.
So, we know how to prove.
take a walk and come.
So what we're going to learn to do now is, alright, what we're going to move on to is solving more simple trigonometric equations, right? Whatever that means. Yeah?
No.
With us, Smith? With us?
Yeah.
So one thing I realized about this though, that for the close, that's nothing on the there.
Yeah,
Problems. Yeah, exactly. Then close to that. Exactly, that's what it says, yes.
We know that. Yeah?
I was saying that those are small things that confusing those, just also look close and see what we can patterns in this simple.
And if you know what you're looking for, which is factorization and LCM, you know exactly that these are the type of simplification that I'm looking for, so it's easy to find. When you don't know what you're looking for, it's hard to find. Right?
Actually, that's not like
All we did was a homework, which is 9.2. You did them? So, solving simple trigonometric equations. Now, it may feel like deja vu, it's not quite deja vu. Yeah, we have done a topic called solving simple trigonometric equations, but what have we really done in this topic? Let me show you what we have done. What have we done? And this was when we just started trigonometry. And we said, well, how do we usually solve trigonometric equations? And then technically, all we were solving so far was sine of x equal to c. Solving sine of x equal to c, cosine of x equal to c, tangent of x equal to c. And it may look different, but it's not. All I'm saying is that when we were solving, we had things like this. Notice that this is like sine of an angle. That's what I'm trying to get at. Equal to a single thing over here. Right? So this should have been like my x. This should have been like my c. So that's all we have learned to solve. It may feel like a lot, but that's all we've been solving this so far. Right? And there are two ways to solve this. Method 1 and method 2. Right? What are the two ways in solving? What was method 1? Use the graph.
Right.
But when do we use the graph? That's a simplified method. Using graphs of sine, cosine, and tangent. And when do we use this? When sine of something equal to 1, right? When cosine of something equal to, let's say use theta. Make it easier.
0 minus 1.
So 0 or minus 1. When cosine equal to 1, 0 or minus 1. And when tangent of theta equal to Don't lie, 0. And that's the only critical point on the graph.
Right.
Look at the sine curve again. What are the values of the y value? 1, 0, and minus 1. That's why we could use the graph in that case. For the tangent graph, you see, the only critical point we knew of was the 0, because at 1, we would have to estimate what it was. And we don't do the estimation thing. So if it's not critical points on the graph, I cannot use the graph to solve it. So for example, when I said sine x equal to 0, what is the value of theta? Or sine theta equal to 0? It would have been where sine equal to 0. It would have been equal to 0 here, here, and here. And then I would have said, well, those theta values is 0, 180, 360 degrees, or 0, pi radian, 2 pi radians. So, and the same thing for the cosine graph. The cosine graph behaves just like the sine, but it starts at 1 and it just oscillates. So, and then the tangent graph was that. So that's in a nutshell how we would have solved using method 1. Everybody clear, right? Now you have to be clear on this foundation, you know, right? Then method 2 was what?
Quadrant system.
Quadrant system. So when we had the quadrant system, now that we reach that far, we skip out something now, push it straight to the end of the class, end of trigonometry, right? SATC. That's what is the quadrant system. S mean sine alone positive here. A mean everything all positive here, all sine, cosine, tangent. Tangent alone positive here, cosine positive here. But the quadrant system wasn't done until I labeled it appropriately. You're going anti-clockwise, starting at my right horizontal line 0, 90, 180, 270, 360 degrees. But we're supposed to the opposite of theirs. Huh? The opposite of theirs. If you want to say that. And then 0. What is it in radians? Pi upon 2, half a pi. 1 whole of pi. 1.5 pi. And 2 pi in radians, because we have to know that. And then one of the big thing that most of us would have missed out is that 180 degrees equals pi radian. Right? That's how we could have said if you divide both sides by 2, we're going to get 90 here and pi upon 2 here. Right? So that's what we measure angles in radians as well. So that's the only new piece to the puzzle. So, recap one more time. What have we done? We have done solving sine of x, sine of a single angle, or sine of a bracket equals to a single value, cosine of something equals to a single value, cosine, tangent of another thing equals to a single value. That's all we have done. Now, where are we going? Sometimes, the man is not going to give us this. The man is going to give us a long equation that don't just have sine alone sitting on one side of the equation and a single value sitting on the other side. And then we have to go through some manipulation to get it down to this. What I want you to know is that we will always be coming back to this, right? And if you don't know the foundation, you're not going to be able to solve any trigonometric equation on the face of the earth. Right? So let's use some of the identities and start solving more not so simple trigonometric equation. You know? But they were all being templates. So let's see what the first set of equations we are responsible for. Right? All right. So that would be the first item we're going to be looking at. Now, remember we said that the syllabus specifically say that we must always assume that the angles are in radians unless otherwise stated. This is otherwise stated. You can see there is degrees there, so we'll work in degrees and ensure that our calculator is in degrees more, right? For the newcomers, let me point out the difference here as opposed to what you did in fifth form, so it's clear. In fifth form, we would have simply said sine inverse both sides. What we're saying is that that's not enough anymore, because that's giving me one answer, and Mr. Keith is always interested in all possible values, right? So we're going to get multiple solutions, and this is the way that we will get multiple solutions, right? So when you watch the video, you should be seeing that coming up, right? So in this case, what I want you to know now is that there are some rules in solving trigonometric equations, right? Basically, two basic rules. What are the two basic rules? Two basic rules is that one, unlike when I was proving trigonometric equations and I need sine and cosine only, what I need most importantly when I'm solving a trigonometric equation is that the equation has only one trigonometric ratio. That means it can be sine alone. So in this case, this thing not allowed. Two of them in two bull in one pen can't work, right? The angles must be the same. That means, let's say for example, I saw 2x here. I would say I am dealing with two different angles and that could work, right? That means we would have to find a way to change that 2x to single x. Later on, you're going to see how we change that, and that is called double angle. Right? And that's pretty much it. So you can have sine alone, cosine alone, tangent alone. You can even have secant alone. What matters is that I don't see secant and sine. Right? I can have cotangent alone. Yeah. I just don't need to see more than one. Right? And if I see more than one, chances are I won't be able to solve it. There are exceptions. There are always exceptions. Like 1 in 100 on the exam. Right? Like if I see sine of x times cosine of x equal to 0. It means this is a product. That's a different thing. Because this is one term. A times b equals 0, that means either a equals 0 or b equals 0. So it would come out down to the same thing. Fair enough? But generally speaking, if we can help it, we must see sine alone, cosine alone, tangent alone, secant alone, one trigonometric equation alone with a single angle. The next thing that we typically point out when we're solving trigonometric equations is that if I have more than two terms, notice here, I only have two terms in the equation. See? If I have more than two terms, chances are to come out to be a quadratic in the end. Right? So here's the thing. In this equation, because we know that the only rule must have a single trig ratio and a single angle. So because we know that the sine and the cosine can't sit beside each other in the same equation. So what do? We need to either change the sine to the cosine or the cosine to the sine. Now, can we change the sine to the cosine? I'm going to tell you that you should say no. And why can't I change it? Because the identity that I know is sine squared of x plus cosine squared of x equal to 1. Yes, I do have an equation with sine and cosine alone. That means I can transpose that equation to change cosine squared of x to 1 minus sine squared of x. Now, so why did I say I can't change sine to cosine? Because if I did, I would end up with a square root of 1 minus cosine squared of x, and that too ugly and complicated, right? So all the time we say, yes, we can change sine to cosine, or cosine to sine is if that thing was squared to begin with, right? So if it wasn't squared, I say I cannot change it.
It's like still looking at the one that's more complicated. Because as a square sign and the...
No, that's not the reason. Well, I wouldn't say it that way. I would say all the trigonometric equations, ratios that are squared can be changed to another, right? Because even the other equation that we derived, you realize that the secant was squared in that identity, right? All of them must be squared. I'm going to deal with that sometime. So, we can't change the sine to the cosine squared, but luckily that cosine was squared, and therefore I can change that to the sine squared. So, cosine squared of x minus 3 sine of x minus 3 equals to 0. Because I know that I need to change the cosine squared. Remember now, cosine squared needs to be contained in our bracket because cosine squared was initially 1 thing. So it's 2 times whatever cosine squared is. That means the 2 must multiply whatever cosine is. That's why I need to put it in bracket. 1 minus sine squared of x. That's a common error, that's why I stress it so much. Minus 3 sine of x minus 3 equals to 0. Note, everything is now in terms of sine. So this is now twice minus twice sine squared of x using the distributive law. 3 sine of x minus 3 equals to 0. And this can be further simplified to minus 1 equals to 0. Now, what I want you to start recognizing that this is technically a quadratic. But I don't want this like this, by the way. Why is it a quadratic? Let me show you what a quadratic looks like. May I erase this side?
A square equals to 0.
So for quadratics, right? I usually have x squared plus ax squared plus bx plus c equals to 0. Is that true? It was a times something squared plus b times that thing that was squared plus a constant. That's all. And when I was solving this, I can either use factorize and set to 0. That's all. When I'm solving for x. Or I can use quadratic formula. That's all. The quadratic formula would have been x equals to minus b plus or minus the square root of b squared minus 4ac all over 2a. That's all. This was a quadratic in x. We say this is a quadratic in x because x was being squared and x was sitting by itself. In this case, it's a quadratic in sine. I'm going to show you. Sine of x. But another thing is that when I write a quadratic equation, the term with the highest power, when I write any polynomial, which is adding powers of x or powers of something, right? I want the term with the highest power to have a positive coefficient all the time, right? So because this thing with the square have a negative coefficient, I will do one of two things. I will either multiply both sides by -1 or bring everything to the other side of the equation. The other one is easier, right? So if I bring this over, the equal sign, it comes over the plus, that we usually say, right? So we're leaving nothing on this side, because everything needs to be on one side when we're solving a quadratic equation. So, and 0 and an x. So this would have been twice sine squared of x plus, but this also come over 3 sine of x, and this go over plus 1. So then I will say, just so that we can all see, what is sine squared of x? it's really sine of x squared plus 3 times sine of x plus 1 equal to 0. So can you see that this is like a x squared plus 3x plus c? It's a quadratic in, right? In 1. It's a quadratic in sine of x. So unlike this one, where I would have put x equal to minus b plus or minus, right? I would have to say sine of x is equal to minus b plus or minus the square root of da da da, right? To make it clearer and simplified in the exam, I will always recommend us making a substitution and say let, for example, y equal to sine of x. And then this becomes 0 equal to 2y squared plus 3y plus 1. Everybody follow so far? So, recap before we continue the solution. We got a trigonometric equation, and in order to solve it, I need to see one trig equation. I was seeing both sine and cosine in the same equation, and that's not allowed. We cannot change sine because it wasn't squared, but we can change the cosine because it was squared. Using sine squared plus cosine squared equal to 1, we got that cosine squared was equal to 1 minus sine squared. No? So we replace cosine squared with 1 minus sine squared. Then we realized that everything was in terms of sine alone, and all the angles were agreed. So we were in good standing. Then we realized that, hey, this is really a quadratic, you know. So I want the term, so that it's easy for me, I want the term with the highest power to have a positive coefficient. And that's what dictates my transfer everything to one side. So that's what I did. Or you can say I multiply both sides by negative.
You're not supposed to say negative.
Huh?
You're not supposed to be negative.
No, but I bring everything over as a negative. Remember what I said just now? My preference, and your preference should also be that I don't want the term with the highest power to be negative. So, and it's not illegal to bring everything over to one side of the equation, or to multiply the entire equation by -1. So multiply this by -1, that changes to positive. Multiply that by -1, that also changes to positive. Multiply this by -1, it changes to positive. Multiply 0 by negative, it stays 0. So it's not incorrect. That's true? Then I said, well, for me to clearly see that it's a quadratic, I want to get rid of this sine x. So I make a substitution. And I said, let y equal to sine of x. So this becomes 2y squared plus 3y plus 1. No, this is definitely a quadratic equation that we could have handled in Sept. Do you agree? All right. And what are the two methods? Factorize or finding LCM. You can follow the LCM or use the quadratic formula, right? So I will resort to the quadratic formula only if necessary. So I always try to factorize first. There are many ways of factorizing. There is the AC method. There is box method. There is writing down the answer using the rule that first give first, last give last. Last sign is positive, that means both signs are the same. There are enough methods that you all will have learned in Sept and ADMAT. Anyone that you're most comfortable with, stick with it. Please don't. Fair enough? So the way I think is most intuitive and very procedural, so you won't make mistake in the exam, is the AC method. So I'm just going to run that one. Fair enough? But if anyone you comfortable with, just put it on the paper. I know all of them. Fair enough? All right. So this times this. This is 2. That's all. What are the factors of 2? 1 and 2. And as a matter of fact, it could be -1 and -2 too. But remember that because this sign is a plus, this is just another addition to the AC method to make it better, right? Is that because this last sign is a plus, that means I know that both of these things must be the same sign, negative and negative or positive and positive. But which one is it? Take the color of that one. So I know that it's plus and plus. Or you can just leave it like that and say, what do I do with it? Do I add or subtract them? And you'll have realized that I add 1 and 2 to get 3, positive 3. So I'm in good standing. Fair enough? So having found that, I'm going to rewrite the middle term. Let's go over the AC method one more time. I multiply the last and the first. Clearly, the terms must be in decreasing order of y or x. 2, then 1, then 0. Right? Multiply the last and the first, I get 2. Try to factorize that product and see if I can add those factors or subtract those factors to give me the middle term. Whichever factors that can be added or subtracted to give me the middle term, that's the one that I want, right? Then this becomes 0 equal to 2y squared. So I'm rewriting the middle term using these two, plus a single y, plus 2y, plus 1. Right? I hope it's all coming back to you now, right? Then I will keep these two technically and I will factorize something out of them. Y can be taken out of this, leave me with 2y. If I take out 1y, 1 of the y is left and 2 is left, right? Plus, if I take out a y, just a coefficient of 1 is left. Anything that is in that bracket needs to be here. So that's a nice little check, right? Then what would I have taken out of this 2y to make that plus 2y? Well, clearly I have plus 1. I will factorize in by taking out common terms again. So 2y plus 1 is a common thing to these two terms, right? What is left? A single y and a plus 1. Is that true? Then I remember that if I multiply two things that give me 0, either one of them must be 0. That's all? So either 2y plus 1 equal to 0. Therefore, y equal to -1. I bring over the -1. Divide both sides by 2, -1/2. Or y plus 1 equal to 0. Or what? That means y is equal to -1. Are we good? The question is, did the man then give me any equation with y in it? So can I give them y as the answer and set up that up? No. Man then give me values of x. I introduced this y. So now I have to resubstitute that y, right? But y we had set the sine of x. So now I'm getting, therefore, it is sine of x, the y, is equal to -1/2. Or it is the sine of x, which is the y, is equal to -1. Notice, guys, that I have successfully gotten what I want, which is sine of something equal to c, sine of something equal to c, right? And we should be comfortable with solving those. You know?
Don't erase anything.
So
Everybody clear?
will they always be quadratic?
Most times than not. At this, yeah, most times. Let me just put that down. As a practice, you have 2 minutes to finish solving that equation. No, we're not done yet. We have to find values of x. Remember, we said solve the equation. So I need to say the x values, right? I was saying in fifth form, what you would have done at that stage was to say sine inverse, but that's not enough at this stage, right? One answer. Yeah, everybody's supposed to finish the work, you know.
No,
In 2 minutes, right? 2 minutes almost done. Nothing wrong. That's big forward. But this is going to be one solution. How many solutions are we looking for? A lot of solutions. What are the 2 ways we know to solve those? Solve that big amount now. The graph or the quadrant system. If you don't have the graph or the quadrant system, that means you're telling lies, right? Or it's incomplete.
Services.
Go again? We're not going to teach. So when I reach here, guys, everybody watch me, stop writing. When I reach here, what are the 2 ways we know to solve trigonometric equation of this form? Quadrant system or the graph? When do I use the graph for this? No, I use the quadrant system. So what we would have said? We would have said, where is sign negative? It's negative here and here, no? Which is the 3rd and 4th quadrant. What's so special about the 3rd and 4th quadrant? Well, the answers here is 180 plus alpha. That's what this answer is, 180 plus another piece. What's so special about in this case? 360 degrees minus alpha. That's what's special here. That means the only thing we need to find out is the alpha. I would have found my answers, right? Alpha is sine inverse of what? Can't be negative and half. We don't plug negative inside our sine inverse anymore. The negative will tell me we're in the quadrant system thing, right? So
30 degrees.
30 degrees. So the answer here is for x equal to 180 plus the alpha, which is 30 degrees, which is 210, or x equals to 360 minus 30, which is 330 degrees. How many sets of solutions do I need? Only one, right? The next is sine of x equal to -1. And we can use either the graph or, I'll show you we can use this as well, right? If I use the graph, it's the easiest thing though. I use the graph, and I know where the thing is -1, or the 1 place alone is -1. It's not so. This is 90, this is 180, this is 270, this is 360. So what's the answer? 270 by the graph. Right?
Those are the values. Sir, a question like this, how much marks it? I usually how much of these questions because I'm not aware of
The optional question.
There is no option in the examiner. Unfortunately. No option.
So what's the value for this? Match that in. Five marks.
So what?
Spend 10 minutes or doing it.
In which 10 minutes? In which exam? Alright.
Sir, why you say we can't use negative graph?
It's just a procedure. The negative. if you plug in,
That's the value.
plug it in your calculator.
That's the value of the graph.
Plug it in. Minus 30. Minus 30 in the interval of 0 to 360. You see the problem? There's a way to manipulate it, but we don't bother with them things, right? That's too much manipulation. So we just tell you don't put the negative in there. Clear now?
Yes.
You got the 270 because it's in with the -1 in mind.
Where is -1 on the sine graph? -1 corresponds when x equal to 270 degrees. So sine of 270 is -1. Sine of 180 is 0. So where is it -1? At 270.
Sure.
Yeah.
I did it with the quadrant.
You did it with the quadrant system?
I said, if it
You can feel free to do it with the quadrant system because if you choose to do it that way, although at some time you wouldn't be working the most efficient way, you would have been studying one thing. So there's a trade-off. You want to study one thing, that's fine. If you study one thing, or if you study one thing, same story, you know, SATC. Where is sine negative? It is negative.
In the G and C.
Where it's not positive. Angle between the radius vector and nearest horizontal. Right? Then I would say alpha is equal to sine inverse of not -1. Always the positive that I plug in here. What is sine inverse of that? 90 degrees. So I know what my alpha is. The question is, what is the solution when it lies in the third quadrant? Well, this is 180. So this is, and this is alpha. So this is 180 plus alpha. And then what is the solution in this quadrant? 360 degrees minus the alpha. So if I did that, I would have an x equal to 180 plus my 90 as my alpha, that is 270. And then I've got an x equal to 360 degrees minus my 90, which is my alpha, 270. So in both cases, I'm getting the same solution. So is it so wrong to use the quadrant system? No. It's just take a little longer, because you'd have seen that this is the most efficient way. But if you don't care about efficiency, there's enough time in the exam, you can do it using a quadrant system. And now you only have one thing to study, quadrant system. And you can keep the graphs out the door. You don't need them anymore if you did the quadrant system. Here. How would I use the quadrant system? The negative or the positive, tell me where to draw my radius vectors. Then I figure out what is my solutions. Then I find my alpha, and that's it. Then I also need to determine how many sets of solution I need. Remember that? If it was 1x, 2x, that tells me that it's 1 set or 2 set or 3 sets. You know? That's fair, right? Huh? Everybody's good? So much so, going forward, just to make you comfortable, I just use the quadrant system every day and twice on Sundays. You know? One method. You won't need to think about when to use what. You know? And remember, guys, watching the video is not enough, right? You have to ensure that you do the practice work. So that when you're going to the exam, you have your muscle memory. Muscle memory you need in K maths, right? 6 questions, 2.5 hours. So then take some reasoning. So you need the muscle memory to get through the muscle part. That is the part that they repeat every year. You know? But this is the first one, so I appreciate the discomfort with it, right? So let's see if we can get see how much muscle we build from this example, right? Question. Solve for x. Solve for all values of x. Between 0 radian and 2 pi radians. The equation 3 minus 3 cosine theta equal to 2 sine squared of you're doing it. Or just listen to the steps for the second time. One triggeration, meaning to figure out which one you can change, right? Then bring everything to one side, leave 0 on the next. Yes? If it's going more like we come out to their quadratic, we can count 1, 2, 3 terms. Make a suitable substitution. Then you solve that quadratic. Then you resubstitute. And then the rest is history, which is used in the quadrant system to solve. That's it. All the time. See, that's all like 5 marks, sir? 5 steps.
Repeat 5 steps.
Yeah. Let's see what you do in 2 minutes. May I erase everything here? But there's no erase. So, are we finished?
Yes.
Are we close to finish?
Yes.
Alright, let's see how close we were to the answer, right? The first thing we were supposed to do, we got this and say, let's change everything. So, I'm changing the sine square to cosine square because I recognize that the cosine square could be changed, right? Because it was a square, right? Yes? Hello?
Yes.
Yes?
Yes, sir.
The 2 that needs to be in bracket. What is sine squared in terms of cos? 1 minus cosine squared theta. 3 minus 3 cosine theta equal twice times, so that's minus twice cosine squared theta. Where am I bringing everything? To the right or to the left? To the left. Why? Because I want my term with the highest power to be positive. 2 cosine squared theta minus 3 cosine theta, because this was already over here as a negative. This 2 come over as a negative, so this becomes 3 minus 2, that's plus 1, and that is equal to 0. Are we good? Then I will say let y equal to cosine theta. I make a substitution, I can say x, but it doesn't matter what I use. So this becomes 2y squared minus 3y plus 1 equal 0. 1 times 2 is 2. Factors of 1 and 2. But this sign is a plus. See, look at this. If I add them, I don't get positive 3. I get negative 3. If I subtract them, I get 1. That means it needs to be negative and negative. That's by deduction. But there's a rote method where you can say this is the last term is positive. That means the signs on these 2 factors need to be the same, and they need to look like this middle term. So they are both negative. Fair enough?
This side.
Yeah, this. So if this was negative, if the last term, if the last sign was negative, that means one of them is a plus, one is a minus, which is essentially saying subtract them, right? So this becomes 2y squared minus y minus twice y plus 1 equals 0. What can we factor out of the first 2? A y, and now I'm left with 2y minus 1. That means I need a 2y minus 1 here. That means what did I factor out of negative 2y to get 2y and negative 1. So this becomes y minus 1 in one instance and 2y minus 1 in the other. Are we good? So this becomes y equal 1 or y equal to positive a half. Same thing now, I need to, but y is equal to cosine of theta. Therefore, it is cosine of theta that is equal to 1. or it is cosine of theta that is equal to positive 1/2. Using the quadrant system in both cases, SATC, where is cosine positive? Positive here and here in the first and fourth quadrant. I'm seeing alpha and alpha here. That means what is the solution here? It's going to be alpha plus alpha alone right here, no? And then right here is going to be 360 minus alpha. Are we seeing it? Remember, plus, minus, plus, minus. And we have to remember. What is our alpha? Our alpha in this case is cosine inverse of positive 1, which is, what is cosine inverse? 0. So the answer here is that x equal to alpha, which is 0. 0, oh, shoot, I said radians then. So this is 2 pi. So that is 0 radian. What is the symbol for radian? A superscript C, or it's like a degree, but you have cut it off, or you can just say 0 rods. Right? Or x is equal to 2 pi minus alpha. So that means 2 pi minus 0. So the answer is 2 pi. The graph, but if you use the graph, you'd have realized how easy it is. Right? You'd have just got the 0 and 2 pi straight off. But over here, same story. Draw your quadrant system. 0, pi upon 2, pi, 3 pi upon 2, 2 pi. Where is cosine positive? In the first and the fourth quadrant, A and C. Same story again, right? So in this case, my alpha is what? Cosine inverse of 1/2. What it follow? So that is pi upon 3 with your fancy calculator. That is the only way you get pi upon 3, right? And then my answer would be, so theta is equal to, this is alpha, this is alpha. So in this case, x is equal to alpha, right? And in this case, x is equal to 2 pi minus alpha. Same story again, right? So this is just pi upon 3, which is the alpha, right? Or theta equal to 2 pi minus pi upon 3. The calculator can also do that for you, by the way. You don't need to believe with the algebra if you have a fancy calculator. But just in case, how do I get 2 pi to be upon 3? Multiply top and bottom by 3, so I get 6 pi upon 3 minus pi upon 3. I get in 5 pi upon 3 radian. Fair enough? All right. How many persons got that? All right, so it looked like one more for the row. Mm-hmm.
Then what about this one?
Two more for the road. All right? So your character needs to be in degree mode now, right?
Sure. We're moving on. Chase of default 5/3. We work that out.
Huh?
We work with chase of be 5/3.
Alpha equal cosine inverse of a half.
Mm-hmm.
We did that. You calculate in radian or degree.
It's in radian.
Huh?
It's in radian.
It's in radian.
Yeah.
Oh, so but you have a black calculator, so that's the problem. So 5/3, if you press 5/3, press 5 divided by 3. Note the answer that's number 1.0, right? That's that.
Yeah, that's simple.
You just have your fun.
That's already.
Them are the fancy calculator. Natural view, right? Alright. Alright.
You work on get that one then.
Yeah man, you need to work on get that one. Alright?
Sir, this
So-
one is a good one.
No,
Only the fancy ones.
not very fancy.
The much of the fancy one though.
2.5 or something like that. Oh, no. Press. How many persons don't have the fancy calculator?
Almost in there.
It looks so. All right. So solve for this. 2 more minutes before I start working on the first one.
Over 3. No, right beside.
Yes, fine. All right, you're confirming for both these students, all right? Anthony? Ashton? Yes, sir, both days. Andre?
Yes, sir.
Both days? Yes, sir. Douglas? Fred? Fred? Dana Ferguson? Shannon Morrison? All right. Shane? Karika? Suko? Giovanni? Gordon? Celia? Graham? Paul? First Ford?
Both.
Huh?
Both.
Michael?
Both, sir.
Can't you remember the faces then? Peter? Arla? Yvette? Julian? Brandon? Brandon on? You're both.
Didn't hear my name.
Who that?
Craig.
Huh?
Craig.
Your last name, Craig?
Rochester.
Huh?
Rochester.
You usually hearing here? You usually hearing here?
Not my second. No, it's my third class. I switched over.
From Tuesday?
Yeah.
Huh? So you'd have been in my Tuesday class? Huh?
Yep.
Well, then never switched over, you know. So I'll need to add it to the screen, okay? Craig Rochester.
Yes. Rochester.
I'm gonna guess. Give my number.
Phone number 291 65
Huh?
6560
Thank you. And it's the third class in this Saturday class. So you guys finished 5.1 yet? Finished? You guys successfully got it into one trigger ratio already, right? All right, so let's take a look. All right. So part A, we have 2 cotangent squared of x plus cosecant of x equal to 1. Right? Now, the first thing I was always try to do is to change. If we see 2 tricks in the same equation, and I'm solving the equation, I need to try to get one of them to change to the other, right? Now, the question is, which identity do we know? Well, all 3 will be on the formula sheet, by the way. So you can quickly scan through the formula sheet, and you're seeing an equation that has both cotangent and cosecant in it. But if you did what I recommended and you just study one of them, and you never even care about the formula sheet, sine squared plus cosine squared of x equal to 1. I said, how can I get cotangent from this? What is cotangent? What's the formula for cotangent in terms of sine and cos? Cos upon sine. So because the sine is in the denominator, I am telling myself divide this by sine. But somebody may say, but sir, if I never choose this and I pick point on this, would I come to the same conclusion? Let's try. What is cosecant? What's the formula?
1 over.
So you see, it's still telling me again to divide by sine. So in both cases, I would have divided by sine. If I didn't remember off about what the identity is, right? Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is what? Cotangent squared, no? And then 1 divided by sine is cosecant. So that is cosecant squared. Huh? Go again? I'm here. This is the identity. You knew that one, right? That's the problem. So you have to watch the videos.
Sir,
right?
how would you know to divide by sign?
So I knew to divide by sine, so I started from this sine square plus cosine square equal to 1 all the time. That's the identity that we need to know and love, right? Then I said, and the other three you could study them as well. But I said that's sometimes too much to study. So I said, well, it's on the formula sheet, you can try that one. Or you can say, what did I divide by? In other words, how do I get this identity to involve cotangent and cosecant? And because I remember what a cosecant is, which is 1 upon sine, I said, well, divide the entire equation by sine squared. This entire equation will be divided by either one of two things, the sine squared or the cosine squared, to get rid of one of them. Right? Good? When you watch the videos, you'll see how it was built upon, right? But for now, that's what we did. We just start with this and divide by sine squared just because of what is in the denominator of whatever point value. Right? So I know that anywhere I see cosecant squared, hold on, but I don't see cosecant squared. So I know that I have to change cotangent squared to cosecant. So I want cotangent squared on one side, and then I bring the one over here, so I get cosecant squared of x minus 1. Everybody follow that? So in this case, this is 2 in bracket cosecant squared of x minus 1 plus cosecant of x equal to 1. Good? Having done that, I expand further. 2 cosecant squared of x minus twice plus cosecant of x equal to 1. Bring everything to one side. But in reducing powers, so I want to put the cosecant of x here, and then I put the minus 3 here. Do you agree with that? Because the one come over as a negative, right? Then I would realize that I can make a substitution of y equal cosecant of x to get 2y squared plus y minus 3 equal to 0. Everybody follow that? Remember, guys, if all else fails, these three formulas are on the formula sheet. Remember, I tell you one more time? So now because you can't remember, you can't do the question, you go and skim through the formula sheet. Fair enough? But I would want you to be able to remember it, right? But sometimes them give a thick booklet for the formula sheet, I don't know why. But that's what they do, right? So, and then, having done that, I need to factorize this, eh? So, 2 times 3 is 6. What are the factors of 6? Well, I could have 1 and 6, but when I add or subtract them, I will never ever get 1. So the next factor is 2 and 3. And I can clearly see that I can subtract them to get 1. So I'm going to rewrite the thing such a way. 2y squared plus the 3y minus the 2y. See, I'm subtracting them. Minus 3. Notice that this last time was a minus, that's why the signs were different. Right? Equal to 0. Then I can factorize further. Y into 2y squared plus 3. That means I need a 2y plus 3. That means I need a 2y plus 3 here. And then what would I have taken out here? A negative 1. That's all. Equal to 0. And then I would have got the y minus 1 into 2y plus 3 equal to 0. Everybody got that so far? Everybody following? Right? No? Who's not following? Come on. All right. So y equal to 1 or y equal to negative 3.5. But 3 upon 2. Good? 1.5. Then I need to go and solve. Well, not quite, because y is equal to cosecant. So this is cosecant of x that is equal to 1. And then this is cosecant of x that is equal to negative 3 all over positive 2. So remember that the negative can only go with 1 up to 2, right? Can go with the top or it can go with the bottom, right? And that's all with the numerator, clear enough? So notice that at the beginning of the class, I told you that we were equipped to solve 3 things. Did I not? I told you that we can solve sine of x equal to c, cosine of x equal to c, tangent of x equal to c. Nowhere did I say solving the reciprocal equal to c, right? And that's because on the calculator, there is no cosecant in inverse. So we have to get it back to sine or cosine in the end, right? But remember what cosecant is? Cosecant is 1 upon sine of x equal to 1 upon 1. Remember what 1 thing is a fraction, the other thing is a fraction. And reciprocate both sides and they're equal still, no? So this becomes sine x, and if I reciprocate 1 upon 1, it's just 1. So sine x equals to 1. Over here, I'd have gotten 1 upon sine of x equal to negative 3 upon 2. Reciprocating gives negative 2/3. Can you see that? Here, you can use the graph or you can use the quadrant system. So whether you use the graph, SATC, the quadrant system, positive here and here. Sine inverse of 1. 90. Then this would have been x equal to alpha, which is 90. Or x equal 180 minus 90, which is 90 degrees. Or you can just use the graph and you get 90 degrees, right? Over here, this is clearly a quadrant system solution, SATC. Where is sine negative? Where it's not positive? In the third and fourth quadrant. This is alpha, that is alpha. What is alpha? Alpha is sine inverse of positive 2/3. What did that come out to be? In degrees. What is that? Guys, you just did the question?
41.81.
41.81. 41.81.
Degrees.
So this is x equal to 180 plus the alpha, which is 180 plus the 41.8, which is what? 221.8? Is that correct?
Yes.
And then x equal to 360 degrees minus the alpha, or 360 degrees minus that 41.8. What did that come out to be? 318.2 degrees. Good. That was it? Yes, sir.
You are factorizing correctly, sir?
Yeah.
Or instead of getting 3, you get 1. Yeah, that is quite fun. What you did was to disregard the LCM of your finding. That's all. Alright, that works. I mean, you'll be comfortable with 40. That's what they are going to require.
Part B, another 3 minutes.
said earlier.
Third question. Come on, table justice. We work it away out, like change out the cotangent and the cosine. Now, the step is like sine and.
You could, but then you realize that you have to you have to find you would have both sine and cosine and you couldn't do nothing about them, right? You agree? That I couldn't. Oh yeah, you could have.
So we don't work it first.
Yeah, and it would have worked, but you were stuck on that way. Really call them mistake. Yeah, so why you stuck?
I didn't start a question and ask you one word.
No, but you're the right stuff. What is this? You know that the two multiple numerical, you know that, right? So that's going down. You start with that, right? Technically, you should have to do this one. You agree? And after that, you can find everything of the whole thing. Sine squared of it. Yeah? This sine squared is from 1, right? So this is equal 1 and 1. Yeah? But you have practice here. Means you got a form, but you cannot create something different. You see, many ways to go around about it, right? Sure.
On the right part? Ah, on the right part of here. Figure out what you do after this. Where you start sketching out.
Where you started? You need to understand it to start.
I just party alone, I just learning this meaning for the like this first word, make a meaning for it.
When we look at that question, part B, the first thing we realize is that A, none of them are square. So none of them can technically be converted to each other, right? So you have to just go and say, all right, what's the next step? Because I know of a fact that I can never solve all of that with three different triggerations. So I have to just start convert and survival mode. So we'll convert everything. Well, you're going to say, well, is it possible, though, to change at least two of them to involve one of the third? And we realize that, hey, secant, well, only one thing secant can be changed to one. Cost. And then I see that it match over here, so. And then I say, well, tangent can also be in terms of cost. You just have to introduce something that I don't necessarily want, but I'm going to do it because we have no choice. Fair enough? So, in this case, I am saying 4 secant of x minus tangent of x equals 6 cosine of x is 4 in bracket 1 upon cosine of x minus sine of x upon cosine of x equal to 6 cosine of x. Everything is a fraction, so why not make everything a fraction? Everything on this side. I can find the LCM of the whole thing. What's the LCM of the whole thing there? Cosine, a single cosine. So use cosine square, but it doesn't matter. We'd have simplified and it would have been alright. So if I use cosine of x into cosine of x equals 1. 1 times the original numerator, which is 4 times 1, which is 4. Yes? Minus cosine into that. Sine of x equal to 1 into cosine of x equals cosine. So this is 6 cosine squared of x. Why did I think that you're under? Let me see what you did again. Multiply everything by cosine squared. See.
if you multiply everything by cosine squared, that's an equation, so I am bound to multiply over here by cosine squared. You need a cosine cube, which is a problem. You're not you wouldn't want to keep, right?
So, you follow this? Everybody's good? Then, what do I know about find the LCM of an entire equation? What can I do with that LCM? I can disregard it because everything is upon the same thing. So, that's a typical way of solving an equation that involves fraction. Find the LCM of everything because nothing can be solved in the denominator. Find the LCM of both sides of the equation, you know, and then just throw the LCM. It's as if it's not there, right? So, in particular, I have my 4 minus sine of x equals to 6 cosine squared of x. Now you realize that, all right, it's looking more like something that I can work with. Fair enough? I can now change cosine squared to sine, no? So I get 4 minus sine of x equal to 6 in bracket 1 minus sine squared of x. Yes? So now I have 4 minus sine of x equal to 6 minus 6 sine squared of x. Bring everything to my left-hand side. I will get 6 sine squared of x minus the sine of x that is over there already. The 6 come over as a negative. To join the positive force, I'm getting a negative 2 equal to 0. Everybody follow that? Yes?
Or the cost, repeat that, the cost turn to 6. If you get the 6 line out there.
What is cosine squared in terms of sine? Is it 1 minus sine squared? From sine squared plus cosine squared equal 1? Yes? And remember the aim was, I am still trying to get one single trigonometric equation, or trigonometric ratio in the equation. Right? Then I say let y equal the sine of x. So I get 6y squared minus y minus twice equal to 0. What are the factors? Well, this is negative 12. What are the factors of negative 12? Well, it's either 2 and 6. Or it can be 1 and 12, which is clearly not it, because I need to subtract or add to get 1. It can be 2 and 6. I know it's 4 and 3, but I need to show you a systematic way in the exam if you're under pressure. You just go through 1, 2, 3 until you find the right factor. You see what I'm saying?
I give you the same sign.
And then this is 3 and 4, and then clearly they can be subtracted to give me 1, right? So in this case, I'm getting 6y squared, and because the negative is the overall, the bigger one is negative, plus 3y minus 2 equals to 0. What can be taken out of this? 2y. We'll take out 2y to that, then 3y is left here, and then minus 2 is left there. That means I need a 3y minus 2 over here. That means I take out a plus 1 equals to 0. So 2y plus 1 or 3y minus 2 equals to 0. Everybody follow? That means y equals negative a half or y equal to positive 2/3. Why are you making up the face, miss? What up? You good? All right.
In terms of using y as substitution, why is the only thing I could use a or with?
You can use p anything you want. All right. So now we have to remember that, but why we are made into sine of x, that means it is sine of x that is equal to negative a half, or it is sine of x that is equal to positive 2/3. Quadrant on the wall where is sign negative, it's negative where it's not positive. Here and here, again, sine inverse or alpha, sine inverse of a positive half is what? Huh? 30 degrees. So 30 go there, 30 go there. Reading of my solution, or 180 plus another piece. So x equal to 180 plus 30, 210. And x equal to 360 minus a piece, 330 degrees. And then over here, same thing. Where is sign positive this time though, in the first and second quadrant? What am I interested in? Then what's my alpha? Sine inverse of 2/3. When my calculator is in degree mode, what does that give me? 41.8. Same thing that last. 41.8. 41.8. And so x is equal to 41.8 degrees, or x is equal to 180 minus this piece, which is 118, 128, oh God, 138.2 degrees. All right, that's it. What's the concern? No concern? So, homework 3.3. What page is try these 3.3 on? Give more 3.3, 9.3. Part C, you're not finding general solution. You're solving. Is it theta or x that is there? Theta. You're solving for theta in the interval 0 to 2 pi radian. So you're finding specific solution, not general solution. So don't tell me that you can't have part C. Clear up? I've not done general solution. Right? Everything above done so far is called specific solution, because we find a specific value for theta, we find a specific value for x. Right? You are doing part C, but you're solving for not general solution, you're solving for the specific solution, which is the normal way. Right? Clear?
Instead of degrees, radians.
That's basically what I think.
No. For part A, you realize part A is solved between 0 and 360 degrees.
Yeah.
Part B is a different question altogether. And part B, I'm saying I want it in radian. Clear now? Crystal clear? Alright. What are you packing up to next? So we'll let you out. I just need you to get something so you can start assimilating, right? For next week, Sunday. So let's give you a little window into where we're going next week, right? In other words, I'm giving you some subs to swap. So by next week, Sunday, everybody's supposed to know that. right? Yeah? So the first identity we have learned so far is sine squared plus cosine squared equals 1. That's the main one, right? And then you can derive other stuff from it. The next thing that we're going to be learning is compound angle formula. Now, compound angle formula is very, very important, you know, because you're going to realize we're going to use compound angle formula for all the other topics going forward. It's up here, right? Good? Study 15 times. 1. Sine of A plus B, that's how we call it, compound angle. It's two angles that form one. Let's see how this is expanded. Sine, start with sine. Sine of the first thing, cosine of the second thing. Sine keeps the sign, so I get back a plus, and then cosine of the first thing, sine of the second thing. So you see sine alternate and keep the sign. Start with sine. Fair enough? Sine alternate with sine and cosine. Sine keeps the sign. If it was plus here, give you a plus here. So, and it starts with sine. And it's on the formula sheet. But you're going to use it so much. Can you imagine turning back to the formula sheet 5 times in one exam for this one formula? Right? 2. Sine of A minus B is sine start with sine. So you see the pattern. Sine alternate every day and twice on Sundays. Sine keeps the sign, so it's a minus. And then cosine of A, sine of see A and then B all the time. 3. Hold on. So how you look at the formula sheet? I'm going to show you over here. So you look on the formula sheet, you know. On the formula sheet, it looks like sine A plus or minus B equal to, let's write it so it can fit. Sine A plus or minus B equal to sine A cosine B plus minus in the same order, plus on top, minus on bottom. Cosine of A, sine of B. How do you read it? Well, if I had plus, I would have said A, I read up top. That means I need to read up top over here. So you see that it will pick up plus. That's how you read it, right? 3. Cosine of A plus B is cosine start with cosine. You see the pattern coming up? Cosine start with cosine, but cosine misbehave twice. It comes in doubles instead of alternate. And it changes the sign. Cosine of A, cosine of B, that's why it comes in doubles. And then change the plus to minus, sine of A, sine of B. See it easy when you talk this up? Alright, come again. Number 4. Cosine of A minus B is cosine start with cosine every day and twice on Sundays. Cosine of A, cosine of B, but it changes the sign from minus to plus, and then this is sine of A, sine of, right? And then your homework, part of your homework is to write how we look on the formula sheet using that pattern. And then number 5, tangent. Tangent of A plus B, this one is a little ugly. Tangent of the first thing plus tangent of the second thing. Know that in the numerator it appears to keep the sign. And the sign will alternate thereafter. 1 minus tangent of A, tangent of B. Number 6. Tangent of A plus B is equal to tangent of minus tangent of A minus tangent of B all over 1 plus, see, it starts with minus, then it changes to plus, tangent of A, tangent of B. And then you're going to also show me how it look on the formula sheet, how you expect it to look based on that over here. Clear enough? All right. Have a good one.